In this section, we learned about one of the most important filters in control theory, the Kalman filter. In essence, we have a mathematical proof that given the right assumptions, the Kalman filter is an optimal filter. What do I mean? That there is no other filter that will give me more accurate results about the system state than the Kalman filter. The problem is in the sentence, given the right assumptions. The Kalman filter requires certain conditions in order to work. And in the previous section, we saw two such conditions. The first was the linearity of the system, meaning the transition from the previous state to the current state has to be linear as expressed in the F matrix. And the transition from the state space to the sensor space also has to be linear as expressed in, yes, the H matrix. The second assumption is the Gaussian assumption, and this is the big assumption. In order for the Kalman filter to work, everything must be Gaussian with zero mean noise. Zero mean noise means that the chances of being above the mean are exactly equal to the chances being below the mean. The Gaussian assumption isn't so hard to fulfill mainly because of the central limit theorem that basically says if many independent variables are added together, the result will be more likely to be a normal distribution. So we can assume that many complex random processes can be treated as Gaussians. Now, the main difficulty is with the linearity assumption. The Kalman filter, in its simplest, naive form, can't even describe a circular motion. Why? Because a circular motion must be described using sine and cosine function, both are non-linear. What can we do? We will take care of this problem in the following two sections. In the next section, we are going to expand the notion of the naive Kalman filter beyond its linear limitations, what we call the extended Kalman filter. And in chapter 6, we will learn about the particle filter, which tackles this problem in a completely different way. Good luck!